All right, so we are going to be looking at part 2 of chapter 3, which are the last two sections, series, and then binomial theorem. So to start off, again, here are your formulas. I think in this section we should be looking at all the sum formulas and then the binomial theorem. So a series defined is the sum of a sequence. The sequence is always defined here. That is usually an explicit definition. This is your starting I value, your final I value. So that'll tell you how many terms you have in your series. Write out what is meant by each of these. So for letter A, the sum of the series where I equals 1 to 5 of I to the fourth would be 1 to the fourth plus 2 to the fourth plus 3 to the fourth plus 4 to the fourth plus 5 to the fourth. And then let's look at letter B, which is the sum of the series from r equal to 3 to 7 of 3 to the r. So that would be 3 to the third plus 3 to the fourth plus 3 to the fifth plus 3 to the sixth plus 3 to the seventh. And some people get confused and think that the value on top is how many terms. It's actually the ending term. So this is my first R value. This is my last R value. So it's not the amount of terms. Write the sum in sigma notation. So these are a little bit difficult because you have to figure out your own rule. You'll notice up top the numbers start at 1 and they increase in order at, consecutively, and then the denominators start at 2 and do exactly the same thing. So if I start at I equal to 1, then I could actually put I on top divided by I plus 1. And because I'm using I equal to 1, that means my ending term would be 99 because I on top ends at 99. That would be my sum in sigma notation. Find the partial sum for the first 50 terms of the sequence. Well, if you notice, this is an arithmetic. So things that you'll notice is if they're going to ask you for a sum of something like the first 50 terms of a series, then it's probably going to be either arithmetic or geometric. So in this case, we can use the formulas that were given to us. So there's two formulas because, where is it? This one is not as common because this one you need to know your first term and last term. But a lot of times you're not given the last term. So if you notice here, there's ... saying we don't know the last one. We're not going to give it to you. So what you essentially are doing is using the u sub n equals u sub 1 plus n minus 1 times d. They're substituting that into this formula for you. Well, into this to get this formula, which you'll notice as long as you know your n value, your u sub 1 value, and your common difference, then you can find the sum. So for this, we have that u sub 1 is 3. My n value, I want the first 50 terms, and my common difference we found was 5. So the sum of the first 50 terms would be the n value, 50, divided by 2 times the first value, plus n, which is 50, minus 1 times the common difference of 5. Make sure that you do order of operations properly because this is the outside set of parentheses. So inside has to happen first. The partial sum for the first 20 terms, in this case, you'll notice they're multiplying by 2. So this is geometric. So the formulas that are there, there's the sum of a finite, sum of an infinite. Because we're finding the first 20 terms, this is finite. If I could spell. So again, two formulas are given. It really doesn't matter which one you use because if you notice, they both need u sub 1, they both need r, and they both need the n value. So I'm going to use the first one that's there just because it's the first. If I want to find the sum of the first 20 terms, that would be u sub 1, which is the first term, 3, the common ratio, which is 2, to the nth power, which is 20, minus 1, all over r, which is 2 minus 1. So you could simplify that easily to find the value. Infinite geometric series. Those are where your sequence does not end. And we talk about geometric series because you could actually have the sum of the sequence, which is the series, be or limit to a value, which would be convergent, or you could have it not have a limit value, which would be divergent. So a convergent series, geometric series, happens when your r value is less than 1. So if you think about it, when your r value, absolute value of r, what that says is that your r value can be anything between -1 and 1. Essentially, if you take a sequence that's geometric, so multiplying by a value that's where the absolute value is less than 1, you will end up with the sequence itself limiting to the value of 0. So in the end, you're essentially adding nothing. You start by adding a value, but the value you add gets smaller and smaller until the value that you're adding is close to 0. So that would be considered a convergent geometric sequence, which then the series is convergent. Did that even make sense? Divergent would be obviously if the absolute value of r is greater than or equal to 1. So those would be the values outside of -1 and 1. Not exactly sure what happened there. So this problem usually shows up for most infinite geometric series. A rational number is a number that can be expressed as a quotient of two integers. Show that the repeating decimal is a rational number. So you can actually create a geometric sequence out of that because 0.66666 and so on. What you're really doing is taking the value, one more, of 0.06. That would be exactly the same thing as starting with the value of 0.6, adding 0.06, wow. And then you just keep moving the place value and adding in the 6. So I'm going to do this in fractional format. So that's 6/10, that's 6/100, that's 6/1000, and so on, 10,000. So what you'll notice is this is 6/10. This next value, it's 6/10 multiplied by another tenth. And then this is 6/10 multiplied by 1/10 multiplied by 1/10 again. And the last one would be 6/10 multiplied by 1/10 times 1/10 times 1/10, which is obviously to the third power. So you should see that the sequence is multiplied by a tenth. So my a sub 1 is equal to 6/10. My r value is obviously 1/10. And then we can use the formula that we had before. And so the sum of an infinite geometric sequence would be the formula up there. So our r value is definitely, the absolute value would be less than 1. So I can actually find the sum of the infinite geometric sequence, meaning if I was to keep going and add up all these values, you would be getting the quotient or the rational number that represents 0.6 repeating. So S sub, and in this case there's no S sub, it's just S, and I wanted to change my color. The sum would give us the actual rational number that is represented by 0.6 repeating, would be the first value, which is 0.6, divided by 1 minus 0.1, which would be 0.6 divided by 0.9, which is obviously 6/9, simplified to 2/3, which we already knew that 2/3 was the answer, but these definitely do get a little more complicated where you wouldn't know the value right away. Example 19 has an example of a geometric series. If a ball has elasticity that it bounces up 80% of its previous height. All right, so let's give myself a line. So my ball starts here, bounces, so I'll start here, jumps down, bounces 80% of the height from before, 80%, and so on. You get the idea of what's happening? Find the total vertical distance traveled up and down by this ball when it's dropped from an altitude of 3 meters. So its initial height is 3. Ignore friction and air resistance. So let's see, what do I want to do? I want to see the total vertical distance traveled up and down by this ball when it is dropped. So I'm going to have to reason through this a little bit. I didn't mean to write that. So vertical distance, so that is traveled down and up. So this vertical distance right here going down would be 3. This vertical going up would be 3 times 0.8, which is 2.4. On its way down would be 2.4, on its way up, and so on. So understanding the fact that you're doubling some heights, we're starting with a height of 3 plus 2. We're going to double all the rest of the heights. So my next height would have been 2.4, or it actually, would be 2.4 plus, then the next height after that would be 80% of 2.4. Then the next height would be 80% of that. So really I'm taking the 2.4, multiplying the 0.8 already, but then I'm doing it again. And then I would do it again and again and again. So what you'll notice is inside of here, this is the geometric sequence. It's very confusing because you would have had to really look at the image and understand that the heights, you're not simply adding a geometric series, you are bouncing up and down, so you're actually using the heights twice. So what I have inside is that the U sub 1 and then the R. The R is 0.8. The U sub 1 would be the 24 that we start with. So this would be when n equals 1. This term here would be when n equals 2, and so on. So my sum would be U of 1 divided by 1 minus R, which gives me 12. So that height was 12. The total distance would be 3 plus 2 times my 12, so 24 plus 3 makes 27, which would be in, I believe, meters. I found this one to be a kind of confusing problem, which is why I wanted to do the example for it. Binomial theorem. So this is actually a pretty easy and quick section. We're going to start off with understanding Pascal's triangle, which will be very helpful. And I can't remember if I have a page for that. I do. So a binomial theorem helps you essentially simplify anything in this form. A binomial that is to a power. So there's some already written for you down here. Take a look. So several things that you'll notice after looking at it. The ending powers are always the same. The fact that the sequence itself is symmetric, meaning the numbers in front repeat halfway through. The powers of your x's start at 0. This is actually x to the 0 here, going down to x to the 6. And then your y values start with, they actually do exactly the same thing. Let's see what else I could say. I think everything's kind of listed there for you. You can take a read. Pascal's triangle starts with a 1, 1, 1, and then it does the sum in between. So the sum of 1 plus 1 is 2, 1. The sum of these would be 3, some of these would be 3, and then 1, 1, 4, 6, 4, 1, and so on. This is going to help to find the coefficients. So use Pascal's triangle to expand 2k minus 3 to the 5th power. So I'm actually going to erase Pascal's. I'm going to move this up so we have a little more room. And I'm going to neatly write it again. So we get the 5th line is what I'm looking for. So here's the line I'm going to need. So those are my coefficients. So I'm going to write them as a list instead, just so that you can see it a little bit easier. The coefficients will be 1, 5, 10, 10, 5, 1. My x values, or my a values, in this case, this is a, and this is b. So a is equal to 2k. B is equal to negative 3. So my a value would be here. I'm just going to write them all down because I'm going to take them all to a power. So where am I? My b's we'll do in pink. I'm leaving a little space for my exponent, that's why. And then you are essentially doing your powers as such. So my a value, I can start the power at the highest and then decrease by 1. And you'll get all the way down to 0. The other one can start at 0 and increase up to 5. What you'll notice is that the sum of the powers always adds up to 5. And if you do it correctly, it will do that every single time. And then from there, some basic rules. Anything to the 0 power is going to be 1. And you're multiplying straight across, so I don't need that term. In this case, each of these terms would be summed to get the entire sequence. So for the first one would be 2 to the 5th times k to the 5th. The second term would be negative 15 times 2 to the 4th times k to the 4th, and so on. So this would be 90 times 2 to the 3rd times k to the 3rd. I don't know why I'm using parentheses there. And then you would just simplify your coefficients. So when you are done, you would sum them all, and that would give you your expansion of that to the 5th. What you're shortcutting is the fact that to do this, you would have to multiply by itself 5 times. Most of you like to use the word FOIL. You would be distributing each binomial 5 different times, which would be a big pain. So factorial notation. N factorial, you just start with n and multiply by 1 decreasing. So the definition here is kind of opposite of the way that I usually do it. 5 factorial will be 5 times 4 times 3 times 2 times 1. I have a habit of going backwards, decreasing my order. Binomial coefficient, we did learn this when we did binomial probability. So this is a combination. This is the same as NCR. So just simply to find 7, let's do 7, choose 3. That would be 7 factorial divided by R factorial times 7 minus 3 factorial. And what's interesting is the way that this always works out. You will be able to simplify this part every single time. So if you have at the bottom 4, so I'm going to actually write it down, 6, 5, 4, 3, 2, 1, 3 factorial, and then 4, 3, 2, 1. because of the way factorials work, you'll be able to cancel the values less than 4 factorial, and all you're really left with is 7 times 6 times 5 divided by 3 times 2 times 1. Makes the math a little bit easier because you will end up having to do some of these by hand. So the answer to the binomial coefficient would be 35. Just so you understand, this is going to be related to Pascal's triangle. And let's see if I gave myself room for that. No, I did not. So Pascal's triangle. Oopsie, 6. All right. And because we did the 7th, I'm just going to get myself down to the 7th term. And then I'll show you the relationship between and why knowing Pascal's can really be helpful. 7, 21, 35, 21, 35, 7, 1. So what you're looking at, and I'll do it right underneath the line, this would actually be 7, choose 0. This would be 7, choose 1. This would be 7, choose 2. This would be 7, choose 3, which is the value we found. And then obviously 7, choose 4. 7, choose 5. 7, choose 6. 7, choose 7. And you'll notice there is symmetry. So 7, choose 0, 7, choose 7 is the same value. 7, choose 1 versus 7, choose 6, same exact value. And obviously I completely made a mistake in my Pascal's. Those numbers are backwards. Oh, I should be using the same color. All right, that makes more sense. So 7, choose 3 and 7, choose 4 are actually the same value. But that's a relationship between the binomial coefficients using combinations versus using Pascal's triangle. Calculate this value. So you're essentially just using the formula that you used a second ago. So for this one, we'll do n factorial over r minus 1 factorial times n minus r minus 1 factorial. So just in case you're confused, the confusion usually comes from the fact that they're using an r inside of. So if I was to do this, I would be calling this A and this A. And this portion is your r factorial, and this portion is the r minus 1 factorial. Just in case if you're confused with the repetition of r. So then they want us to add to that n choose a. So that'd be n factorial over a factorial times n minus a factorial. Let's see. So we know that if I simplify this, let's see. So most of you probably haven't seen something like this, maybe in Honors Pre-Cal. So we're going to prove, all I did was write it a little neater because I know I'm going to need some space. I'm going to be summing up two fractions, so I'm going to try my best to get a common denominator. What you'll notice is factorials are a little bit harder to get common denominators. You have to understand what's happening. So this term and this term are very related. Related meaning this plus 1 means I have one extra term to multiply versus this one that doesn't have the plus 1. So if all I do is multiply the numerator by n minus r plus 1 times n minus r plus 1, these two terms together, right here, would actually give me this term here, okay? Now, the other problem is on this side, I have r factorial, see? This side I have r minus 1 factorial. What happens again is on this term, we actually multiplied one extra term. We have multiplied r on that side. Just to show you what this means, r factorial is equal to r times r minus 1 times r minus 2 times r minus 1 factorial is r minus 1 times r minus 2. So you see that they're exactly similar, but the only thing missing is that the r minus 1 factorial doesn't have the r. So I'm going to multiply this one by r and this one by r. I'm hoping that makes sense to most of you. So right now I actually have a common denominator. The common denominator is r factorial. So what that is r factorial here is the same as this piece here. Those both say r factorial. So r factorial. Then remember I said that the yellow highlight is n minus r plus 1 factorial. So those are my denominators. My numerators are r times n factorial plus n factorial times n minus r plus 1. And then from there, so I'm going to, I don't exactly know how or what the answer is supposed to be. I'm assuming they want another combination. So I notice in the numerator that I could factor out the n factorial. So inside I have left r plus n minus r plus 1. So I factored this term out, and then I used my leftovers, which are boxes in yellow, to write the second part of that term. And then the the denominator, would be r factorial times n minus r plus 1 factorial. Let's see, so this is starting to look somewhat like it makes sense to me. Let's see. In the numerator, if I simplify, I get n factorial times n plus 1 over r factorial times n minus r plus 1. So I'm kind of seeing it. I don't know if you do. If I look at my next step, which I'll do in blue, down here, this n plus 1, I'm going to write first. So I get n factorial. Oh, actually, also, if I have n factorial, then I multiply it by n plus 1, then really what I have is n plus 1 factorial. Meaning the factorial started one number ahead of n. So the numerator actually looks like n plus 1 factorial. The denominator is r factorial times n plus 1, I'm going to put together, and then the minus r factorial. So this is actually the same formula as we had at the very beginning just for the generic combination, where the top is supposed to be n, so that would be here. The bottom would be my choose r. So I believe that should be the answer. Hopefully it matches what's in your textbook. I would take some time with this proof. I'm not sure how often they do proofs on your internal assessment, but it was in the text and it seemed important. All right, so using the binomial theorem, find the expansion for 2k minus 3. I believe we already did that example. Find the term containing a cubed. So if I'm looking at this expansion, I'm going to go down to the 9th. So really, I'm going to deal with the a cubed term. So I know that if I look at the 9th power, so here would be my coefficients. Here would be my negative 3b's. And remember, I did it kind of in an order. I would start from a power of 0, 1, 2, and then here's my third one. This one's, actually, did I do it that way? I'm going to do it that way, just so that it's a little faster. This side, then, I would have to start with 9. Doesn't matter which way you do it. And then 8, 7, and 6. Powers still add up to 9. I think in the other example, I started here with a 9, started here with a 0. You're allowed to start with 0 or start with 9 with either column. Now, the front terms, I don't want to take my Pascals all the way down to the 9th term, because that would take, or the 9th line, it would take a really long time. So instead, what I'm going to do is write it in the combination format. So 9 choose 0, 9 choose 1, 9 choose 2, and then 9 choose 3. I'm guaranteed that this is the line that they're talking about because that would be where my a is cubed. And it says find the entire term. So my entire term, first I would need to know 9 choose 3, so 9 factorial over 3 factorial times 9 minus 3 factorial. So this would be 6 factorial, so the numerator is 9 times 8 times 7. The 6 factorial would cancel with the denominator. This is 3 times 2 times 1, so this cancels to 3, this cancels to 4, and I get 12 times 7, which is 84. Times 2 to the third, which is 8, a cubed, times negative 3 to the 6, which is a positive value, b to the 6. So my coefficient would be 84 times 8 times negative 3 to the 6, and then my a cubed b 6. That would be my complete answer once I multiply out. Find the term independent of x, meaning does not have an x. So if you don't have an x, really, this means the constant term. Independent of x is the constant term. So you'd have to understand how this works. So I'm going to do exactly the same thing that I did a second ago. I'm going to start with 2x squared to the 0 power, and I'm just going to go down the line. And I'm not going to go all the way because at some point I should see a pattern and understand it a little better. This would be negative 3 over x to the 9th. And this would be negative 3 over x to the 8th, negative 3 over x to the 7th. So right now, I have, this is the 4th power, and this is the 7th power. So I'm going to keep going because they have not canceled each other yet. This would be the 3rd, 4th power. And then on this side, in blue, it would be negative 3 over x to the 6th, which you'll kind of notice I already found it. I'm going to erase what's underneath and simplify that line. So what happened was I have 2 to the 3rd, which is 8. X squared to the 6 would be 6 power. And then multiply by negative 3 times, I'm just going to do it to the 6 power. Actually, I guess I could do it all together. Negative 3 over x to the 6 power. Which essentially gives me 2 to the 3rd, x to the 6, negative 3 to the 6, all over x to the 6, because the denominator was x to the 6 power, and that's how I actually cancel the x's. And then my coefficient, this is line 9 choose 0, 9 choose 1, 2, 3, 4, no, just 3. So this is 9 choose 3, which I believe we had a second ago. I think it was 84. 9 choose 3 is 84. So 84 times 2 to the 3rd times negative 3 to the 6th would give me the actual constant term. After that, after this line, you start having x values, but they'll be in the denominator. So this is the only constant term you'll get. And then here, the coefficient of b to the 6th, same thing. I'm not going to finish the problem, but I'll start it for you. We're starting with 2b squared and then negative 1 over b. So this time I think just to change it up, I'll start this one at the power of 12 and I'll start this one at a power of 0. So I have to cancel. And most of you should be able to do this much faster. I'm just going to go down in a list in case you have trouble with this to figure out where they would cancel. This would be 11, 10, 9, 8, 7. So right now I'm a b power of 14. And hopefully I have enough space to get down to an answer that'll work. So 6, 5, 4. So now I'm at a power of 8. And so I'm not going to even write the inside. I'm just going to go like this so you can see. This would be power 1, 2, 3, 4, 5, 6, 7, 8. This is the line where oh my lord, I forgot what I was doing. B to the 6 is what I'm trying to find. So I am essentially, am I there? No, I'm not there yet. Oh lord. So we were at 4 and 8. Oh, I forgot what I was doing. All right, so let me fill these in. And I'm hoping you don't need to write this list every time. I'm only doing it so that you see this. I want to get a total power of 6. So the second column are going to be denominators. So this one, the power of b would be to the 12th. This power would be to the 22 minus 1, so that'd be 21 power. Oh, that's 24, wow. This here would be to the 20 minus 2, which would be 18 power. You can see the pattern already. This would be 18 minus 3, which would be 15th power, 12th power. This would be the 9th power, and this would actually be the 6th power. So this line right here is what I need. Therefore, in the front, I would do 12, choose 6. And that would get me my coefficient of the b to the 6th term. There's the end of the second chapter 3 video.